A be a non-empty subset of Rp, and F on A to R. Now we define partial derivatives for real valued functions of several variables. Assume that A in A is a cluster point of A. For each I from 1 to P, let E sub I stand for the ith standard basis vector of Rp. That is, the ith component is 1 and all the remaining components are 0. In case f sub E sub I A, that is the directional derivative of f at A in the direction of E sub I, exists, we refer to it as the partial derivative of f at A, and write also del f del xi at I, or f sub I A for f sub E sub I of A. Okay? Well, now we have this. Now, that takes us to our second section. This was 2.2 now. The derivatives of functions from Rp to Rq. Now we can start right away with the definition that we have discovered. But here I'll make a simplification. Now for the definition and what follows the definition, we will assume that A is an interior point of cap A. We can do it by assuming that A is in cap A and it's a cluster point of cap A. But then the theorems, the results, and so on, they all become messy because you have to keep track of what vector U points into the set at that point and what not. But if it's an interior point, then all vectors point into the set at that point. And that's what we need for our optimization results. For all the results that we will consider in this course, well, that'll do the job. Now, again, we start with the subset, a non-empty subset of Rp, and f on A to Rq a function. Assume that A is in A interior. We say that f is differentiable at A if there is a linear map T on Rp to Rq such that for any positive real number epsilon, there is some delta positive such that. Now, in here, we had this punctuated delta ball, x different than A, and here, strict inequality. Now, here, since we have gotten rid of division by x minus A in the one-dimensional case, well, if you take here x equal to A, both sides, they will make sense. But what will happen is, well, if x is equal to A, this will become 0, this will become 0 as well. Because this will become f of A minus f of A, that's 0. This will become t of 0, that's 0 as well. So you'll have equality in here if you introduce, if you include x equals A also to be considered in here. Now, to simplify that as well, I will write that in an equivalent form by allowing x being equal to A as well. For all x in B delta A intersection A, we have f of x minus f of A minus t of x minus A. So this is the image of x minus A under the function f. This is less than or equal to epsilon times the norm of x minus A. In case f is differentiable, we will refer to the linear map T in here, to a linear map satisfying the condition as a derivative, but our next proposition, our next result will tell, well, in case f is differentiable, this will be uniquely determined, so we will be able to refer to this as the derivative of f. But it's not clear at the first glance that this might exist, but more than one linear map might do the job. I guess I can erase this part as well. In case f is differentiable at A, we refer to a linear map T with above property as a derivative of f at A. Now, for the next two propositions, we'll omit the proof. Well, that's reachable, that's doable, but you can also check up in Bartle if you're interested in the proof, but we do not wish to lose time by, that would be a too far a digression for us. Now, here, okay, let me write that once more. So let me write them both in one proposition so that I don't have to repeat each time this A in RP, F on A to RQ, a function. Assume that A is in A interior. The first statement, F has at most one derivative at A. This means it may have no derivative, that is, there will not exist any linear map satisfying this, but if it exists, it will be unique. So that expresses that. 2, if f is differentiable at A, then f is continuous at A. Well, this is what we know for real-valued functions of real variables from calculus, but that's also true in general. Proof omitted. But now, when f is differentiable at A, we denote its derivative by dfa. Now this is a symbol as a whole, and dfa, that will be a linear map on Rp to Rq. This is the symbol, well, cap, D, F, and A do not have separate meanings. That as a whole stands for the symbol of this function. But now, we are ready to formalize what we did in here. Then this function exists. Well then, for each u in Rp, you can form this. Okay? This will be actually here cap T of u. But on the other hand, the question is, given a u, does the directional derivative of f at A in the direction of u exist? Does differentiability imply this? Well, it will turn out that differentiability of f at A will imply the existence of this, and in fact, these will be equal to each other. Now, let's consider that result. is in A interior and f is differentiable at A. Now, f sub ua, the directional derivative of f at A in the direction of u is this for each u in Rp. In fact, we have for all u in Rp that df of A evaluated at u is equal to this. Now, proof. Now, let's first consider the situation when u is equal to 0 separately. First, consider the case where u is equal to 0. Then, what do we know about f sub u of A by its definition? It will be 0, that we have seen. And this will be the f of A 0. What do we know about this? The f of A is a linear map. Well, that's then 0 to 0. So the f of AU equal to f sub u of A. Now assume that u is different than 0. Now the way we proceed is, here we will show that the FAU actually satisfies the definition of the directional derivative of f at A in the direction of u. That will give us the result. We said L is the directional derivative of f at u in the direction of f at A in the direction of u if and only if L satisfied a condition. Now, if the condition that L satisfied there is satisfied by dfAu, then that will complete the proof. What we know is that actually f is differentiable at A. Okay? Okay, now let epsilon greater than 0 be. What we need to show is that there is some delta positive such that for all x in the delta, or for all t in the delta ball of 0, if A plus TU is in cap A, that should imply that the norm of 1 over t, f of A plus TU minus f of A minus the f of AU, that is less than epsilon. Okay? But what we know is that this is differentiable. So, well, we will modify the positive real number epsilon. Now, epsilon over 2u, that will also be positive. I will use this epsilon prime when I employ the definition of differentiability. Well, since f is differentiable at A, there is some delta positive such that for all x in the delta ball about A intersection A, we have f of x minus f of A minus the f of A at x minus A. This is less than or equal to epsilon prime, which is this, times the norm of x minus A. I have just written the definition of differentiability. Now, here we need to find some delta prime positive now. Whenever t is delta prime close to 0, A plus tu will be in cap A, and for that, the condition, the inequality in the definition of directional derivative, that'll hold. Now, first, let's consider the following. Let delta prime be equal to delta over norm of u. This will be positive. Now, whenever t is in the deleted delta prime ball about 0, then, well, I claim that A plus tu, that will satisfy the condition in here. That is, okay, A plus tu will be in here. Well, but that's clear. If we have that, A plus tu minus A, that will be the norm of tu, but that's the absolute value of t times the norm of u. But this is now t is, since t is in here, the absolute value of t, that is t minus 0, the absolute value of that, that's less than delta prime, that's u, but that's equal to delta. So whenever t is in here, A plus tu that will be in B delta A if t is in the delta prime ball of 0, but okay, the deleted one is not needed here, but that will use in what follows. So, for any t in this delta prime ball about 0 deleted, whenever A plus tu is also in A, we have what? Now, while we have this, now I can replace x by A plus tu, because A plus tu is in cap A and also in B delta A. So that is f of A plus tu, that's taken for x, minus f of A, minus df of A. Now here x is A plus tu minus A. This is less than or equal to epsilon over 2u times, and this is a plus tu minus a. Okay. What I have just done is, well, I have restricted t to delta prime closeness to 0, such that a plus tu belonged to here, but if it also belongs to cap A, it will belong to here, and this inequality will be valid when we take x equals a plus tu, and that's just what we have written in here. That is f of a plus tu minus f of a. Now what do we have here? These get cancelled. You have df of a tu, but df of a is a linear map. So this is t times df of a u. This is less than or equal to epsilon over 2u. And here we have t times the norm of u. Any questions so far? Okay. So that now t is different than 0. And the absolute value of t thus is positive. So I can divide both sides by the absolute value of t. The sense of the inequality, that will be preserved. So we have then, but the absolute value of t, well, that will actually enter into the norm as 1 over t. So that will 1 over t times this minus, but this t will get cancelled, the f of au. Then here, this will disappear, epsilon over 2u. And well, these u's, the norm of u's, they will get cancelled as well. Here we'll have epsilon over 2, and that's less than epsilon. But what does this mean? For all t in b delta prime of 0 punctuated, whenever a plus tu is in cap A, we have this inequality. But that's nothing but the definition of this here being the directional derivative of f at A in the direction of u. So that completes this. We will now have a simple proposition which will relate directional derivatives, and via the directional derivatives, the derivative of f at A with partial derivatives. Because partial derivatives are particular directional derivatives. So, well, we can use this for having E sub I here. So we have the following corollary here. Now this time, as I will be dealing with partial derivatives, we take this as a real valued map. assume that A is an interior point of A and F is differentiable at A. So we have the same hypotheses as over there, just this R instead of RQ. Now for each I, in 1 to P, the partial derivative of F with respect to xi at A exists. Moreover, for each u in Rp, the derivative of f at A evaluated at u, its value at u is just, you take the ith component of u, you multiply that with the partial derivative of f with respect to xi at A, and you sum these from 1 to P here. This is in Rp. Now the proof is simple. The existence of the partial derivative of f with respect to xi at A for each I in 1 to P follows directly from the above proposition. Y as this partial derivative at A is nothing but, by definition, the directional derivative of f at A in the direction of E sub I. Just take u equal to E sub I. The second part, that's simple but crucial as well. Now take any u in Rp. Now consider the FAU. Now I wish to relate this to partial derivatives. But then the way to do it is to write this as a combination of the standard basis vectors. Well, standard basis vectors do that job for each u. That is, this is dfa summation ui e sub I from 1 to P. This is just u. But as dfa, this is linear. Well, this is now summation. These are real numbers, u sub I, real coefficients. I from 1 to P. But this is just f sub E sub I at A from the above, But by definition, this is just a partial derivative of f with respect to xi at a. What do you conjecture in general if I take a function on a subset of Rp with values in Rq? Can I write its derivative somehow in terms of partial derivatives? Do you remember some result from calculus? Well, partial derivatives are for real valued functions. But now, if you have a vector valued function, then you can consider its coordinate functions. Now, f of a is equal to a q vector. Well, then you can write f sub 1, f sub 2, up to f sub q, such that f sub I of a, actually that just takes the ith component of the q vector, so they will be real valued. Okay, so we can consider the partial derivatives of the coordinate functions of a q vector valued function of p variables. Do you have some conjecture what kind of construct from calculus we can use in relating the derivative of f at a, in the sense here, with the partial derivatives of the coordinate functions? Well, if you take f1 and if you form a matrix by having its partial derivatives in the first row, f2, well, what's that? What's the name of that matrix? The Jacobian. Now, that's what we will reach at in the end. Well, a linear map, dfa, that will be, in the general case, a linear map on Rp to Rq. How can we represent that in linear algebra? By a Q by P matrix, if we represent it, well, say with respect to the standard basis vectors. Now, the Jacobian matrix actually will turn out to be the representative of the linear map, dfa, with respect to the standard basis vectors. So that's actually the agenda for the rest of this section. But before proceeding with that, let's see a couple of examples. Let's say, well, let's take this point. Given that, say, the directional derivative, if it's differentiable at here, since this is an interior point, the directional derivative is defined in each direction. So at 1, 1, we have its directional derivatives in these directions. These are given. Find df 1, 1, 1 at minus 1 to 0. Can you find it? Do we have enough information? Well, we know the derivative of f at 1, 1. We know its values at here, and at here. Okay? Because this directional derivative is equal to df 1, 1, 1 evaluated at 1, 1, 0. Now, if we can write minus 1, 2, 0 as a linear combination of these three vectors, utilizing that the f11 is a linear map, well, then we can rewrite that in terms of the values of the f111 at 110, 101, and 111, that is ABC. Okay, well, I guess I will stop here, but we'll continue with this example, but you can do it without continuing in class. But before that, I wish to make two announcements. One is on all Tuesdays except one, we'll start at 8:40 for the remaining weeks. So I will not remind you of that. I will remind you only if we will do just 1 hour, because 1 week we will be doing just 1 hour if we do not miss